Welcome to part 2 of my lecture on historical and social factors involved in the progress and change in science. Let's get started. So just as a review, recall that advocates of the strong program in sociology of science, as well as other cultural theorists that we've looked at in the previous lecture, argued that scientific evidence does not explain the beliefs of scientific communities or scientific change. Instead, social and psychological factors explain the beliefs of scientific communities as well as scientific change. Things like political factors. And notice that these are non-rational factors. So according to these cultural theorists, non-rational factors explain scientific beliefs and scientific change. And we also looked at a variety of reasons why, that's a problematic conclusion, why some of the arguments that they gave for that conclusion did not succeed. So for example, just very simply put, one reason scientists believe that water is H2O, or that smoking causes cancer, or that drinking out of toilets leads to infection, is that there's scientific evidence that water is H2O, and that smoking causes cancer, and that drinking out of toilets leads to infection. However, there are some positive reasons to evaluate social factors with respect to scientific developments. So as I mentioned in the previous lecture, Thomas Kuhn got some things right, and he was right that we need to pay attention to the history and kind of social structure of scientific communities. We need to look at this stuff. So we're going to look today at some positive reasons to look at these factors. But as we're going to explore, as will become evident throughout this lecture, these positive reasons do not need to replace histories of scientific change that appeal to evidence, okay? So we're going to look at social factors involved in scientific change and as well as the beliefs of scientific communities. But that doesn't mean that we need to say, okay, Galileo believed that the Earth orbits the sun for completely social reasons. No, scientific evidence also plays a very important role in this. And and what we're going to look at today is consistent with scientific evidence explaining the beliefs of scientists and scientific change. So, take a step back though. Let's think about the traditional account of scientific rationality, probably what you learned in your high school textbooks and perhaps in science classes at George Mason as well. You have individuals gathering data, and they'll use various methods to generate justified beliefs about that data, more hypotheses, maybe generate some theories, okay? And the key part is it's always individuals doing the scientific work. And when you read the history of science, it seems just like that. It was Galileo alone with his telescope. It was Semmelweis alone conducting experiments on the effectiveness of hand washing in different wards and hospitals. It was Darwin alone on the Galapagos Islands, documenting the changes and the variation he saw in different species. Okay, so this is a very common understanding of science. In fact, it's an understanding of science that I suspect a lot of scientists themselves believe. Well, here's a plausible claim. Communities of individuals are rational only to the extent that individuals in the community are rational. So, for example, communities of scientists are rational only to the extent that individual scientists in the scientific community are rational. But this leads to a problem, because there is widespread evidence that individuals, including individual scientists, are prone to biases. Cognitive biases, the types of biases that make them irrational on top of that. Does that mean then that the sciences are irrational? If the individual scientists are prone to irrational biases, again, does not that mean that the scientific community itself is irrational? Troubling question. Perhaps the rationality of the scientific community, though, is not dependent on the rationality of the individuals in the community. Perhaps the whole scientific community itself could be rational, even if the individual members of it are irrational. How could that be, though? And this points to an objection. Hey, Davis, if every brick making up my house is red, then my house is red. Just likewise, if every individual scientist in the scientific community is irrational, then the community itself is irrational. It's a powerful objection. And again, Like I said, if all the members of a community are irrational, the community as a whole is irrational. Just like if all the bricks that make up a house are red, the whole house is red. Okay, that's a powerful objection. Or is it? To respond, every brick composing my house is also 2 inches by 2 inches by 4 inches. That does not mean, though, that my house is 2 inches by 2 inches by 4 inches. My house is much bigger than that. Okay, I actually don't own a house. I can't afford one. I live in a condo, but pretend like I do. So it does not follow, then, that just because individual scientists are irrational, that doesn't mean that science itself is irrational or that the community of scientists is irrational, okay? We would need additional reasons, all right? And several thinkers that we look at today make just this point. Science is rational even if individual scientists, being human beings, are prone to irrational biases. So Miriam Solomon, in a book, Social Empiricism, argued that, in fact, not only should we analyze, we should analyze rationality at the level of the scientific community. So we shouldn't even look into individual scientists when we're looking for whether or not science is rational. We should look at the community as a whole. And she argues further that perhaps rationality is a feature of the social organization of scientific communities. So there's something about the way the communities are organized that makes it rational. It's not the individuals in it, it's the way the different individuals are related to each other. So I have a proposal. No, not that kind of proposal. I'd like to propose a proposition, if you may. If all scientists, so here's a way to think about how even if individual scientists are humans, they're irrational, they're prone to biases, the community of scientists as a whole could be a rational enterprise, okay? So here's a proposal. Perhaps if all scientists were reluctant to adopt new ideas, science would stagnate. It wouldn't go anywhere. It wouldn't progress. It wouldn't advance. On the other hand, if all scientists were disposed to novel methods, science would become heavily splintered and well-confirmed ideas would be forgotten. But if there's a mix of these attitudes, this might explain science's progress. So scientists are motivated by a desire for recognition, and so they strive to contribute something new. And science rewards those who correct previous errors or introduce well-supported new ideas. So this protects science from dogmatism. And the fact is, scientific communities, they value self-correction and novelty, but they also value rigorous standards. They value all three of these things. These things aren't intention. They want new things, but they want these new things to meet very high benchmarks of quality. And also, when they do make mistakes, they want to correct those mistakes. Perhaps later this semester, we'll look at some examples of where scientists became aware of mistakes in their generation of knowledge, and they are taking steps to correct it, such as the replication crisis in the medical and social sciences. So David Hull argues that scientists, yes, they are motivated by the desire for recognition, and so they strive to contribute something new, like new hypotheses, or they want to correct previous mistakes, or they want to seek novel perspectives on traditional questions. And here's the implication. Insofar as scientists reward those who correct previous errors, or who introduce new ideas that are well supported by evidence, you can protect science from both dogmatism and stagnation. Philip Kitcher takes it a little bit further. Some big words here called social epistemology. That's just the study of the knowledge of groups rather than individuals. And then the distribution of cognitive labor. So take a shared desire to investigate a phenomenon, and where you have several techniques that look promising. Well, you could recommend that all scientists investigate this phenomenon with just one technique, the technique that seems the most promising, or you could distribute the labor so that different scientists are using different techniques, and then see what happens. For example, suppose we want to determine the prevalence of an infectious disease in a population. Well, we could look at blood samples, and we could have like blood sample drives. We could look at spit samples. We could also look at stool samples. Oh no, not those kinds of stools. So Philip Kitcher proposes that we need a reward system that motivates workers to distribute their cognitive labor across competing programs, trying different techniques, for example, different techniques of detecting the prevalence of a disease in a population. We're also going to look at some feminist critiques of science. So, feminist philosophers of science have made some pretty amazing contributions to our understanding of the development and progress and structure of science in recent decades. So there's strong evidence that obstacles for women entering and succeeding in the sciences in the past has actually hindered scientific progress. And here's, let me tell you one example. So take the field of primatology, okay? Like many fields until recently, it was dominated by men. So these early theories of primate sexual behavior developed by male scientists attributed to females a passive role, to female primates. So social behavior by primates was controlled by alpha male group members, basically. The alpha male in the group is kind of the guy running the show. Well, in the 1970s, Jane Goodall and Diane Fossey started making contributions to the field of primatology. And you've probably heard of Jane Goodall. She's very well known. They made some observations that ended up being far more accurate. They revealed that, in fact, there's actually a far more active role for female primates. Female primates would manipulate male behavior in subtle ways, and they would actually exert control over who they mated with. So then our understanding of primate behavior, it progressed significantly because of the influx of women in the field. And this points to something. This suggests that greater diversity in scientific disciplines can bring more progress to those fields. Basically, increasing the diversity of the workforce in science will increase our knowledge about the world. So there is epistemic value to diversity, as feminist philosophers of science have pointed out. So, lastly, we're going to look at science and values. Okay. So we tend to think of science as being objective, and it's not kind of contaminated by our own moral values. It's something that's independent of it, and to bring our values in would make it kind of messy. On the other hand, though, we criticize. So this makes sense. Like, so for example, when large-scale corporations, we criticize them for their influence over certain scientific fields, because we think corporate interests are kind of contaminating the science. And this is evident. For example, our best medical minds have been accused of devoting their time to researching cures for things that don't seem as important as other concerns. For example, erectile dysfunction, hair loss, aging skin, instead of curing deadly diseases. And the reason why is because there's money involved in treating the above. Pharmaceutical companies have done the calculation, and there's a lot more profit in treating this than cancer. But we would rather them cure cancer. So perhaps then the problem is not with the scientists. Instead, perhaps the problem is the interference of non-scientific motives, non-scientific values, such as financial interests. In fact, perhaps the problem is that human values contaminate science. We want it to be free of these human values if it's going to succeed. So this leads to a question. Can we fully distinguish science from values? Don't we think that science is not the same thing as values? Science is logical, whereas values are connected to our kind of animal nature, our emotional side. These are some fascinating meta-ethical questions about the nature of moral claims in general. But before we even address the nature of just values in general, we should just look at the relationship between them in science. Heather Douglas has argued that we should actually challenge the notion that science should be value-free. And she has some fairly compelling arguments for that. So what is this value-free ideal? Well, it's the idea that social and ethical and political values should have no influence over the reasoning of scientists, and that scientists should proceed in their work with as little concern as possible for these values. I guess they should be like Spock. But according to Douglas, the fact is, science cannot aspire to that ideal. Furthermore, science should not aspire to that ideal. Science cannot be value-free, and science should not be value-free. What does she mean by that? Well, for one thing, scientists are advisors for very important public policy decisions. And values are a key part of these decisions, such as, decisions we made during the COVID-19 epidemic that have impacted millions of people's lives. And the fact is, we want to avoid suffering. We value freedom. We value privacy, innovation, justice, biodiversity, the environment. We fund research that promotes certain kinds of knowledge that we value. So our values are involved in all this. Our values are involved in, basically scientific progress. And our values are involved in what scientists are working on right now. Basically, what scientists are spending their time and research efforts on is intimately intertwined with our values. And that's not a bad thing. It's crucial for what science to focus its attention on. So we want research to be conducted according to certain ethical standards. For example, Budweiser should not test their products on toddlers. Sorry, but it's unethical to test beer on 2-year-olds. So science cannot be value-free then. But not only can not science be value-free, science should not be value-free. So according to Douglas, scientists have a moral responsibility to consider the social and ethical consequences of their work. That might be an error. So the fact is some errors have more costly consequences than others. So suppose there's a low-cost intervention that could potentially help thousands of people. If you implement it and it doesn't work, you've lost a little money. If you don't implement it, but it would have worked, large numbers of people could be injured or killed. Let me tell you a story. What if there was a rabies epidemic in North Dakota? More specifically, large numbers of moose are infected with rabies, and they've been attacking significant numbers of residents. Public health officials have started a campaign to vaccinate all the North Dakotans. But there's other health issues that come from moose attacks, such as broken bones. Moose are very large animals. They stand up to 10 feet tall. They are more deadly than bears. So imagine how dangerous a rabid moose is on top of that. Well, upon looking at the available data about who was bit, an epidemiologist notices 2 trends. None of the bite victims ate onions, whereas the victims' friends who witnessed the attack had just ate onions. The epidemiologist also reads that moose avoid onions when offered them in captivity. They're just not big fans of onions. So the epidemiologist decides to try a public health intervention and encourage residents to increase onion consumption with the campaign, "An onion a day keeps the moose away." So if they try the intervention and it fails, the worst that has happened is that North Dakotans will have increased their onion consumption. If they don't try the intervention, but it would have worked, large numbers of people who could have been saved from moose attacks will be attacked by moose. So this is an example where an epidemiologist ought to consider the consequences of being wrong. And the social consequences of being wrong ought to impact the epidemiologist's decision about whether or not to implement this public health measure, the increased onion consumption diet to prevent moose attacks. Now, just as a note, this is a fictional story. Onions have actually not been confirmed to prevent moose attacks. So the best thing to do is to avoid them if you see them in the wild. So scientists have a moral responsibility then to consider the social and ethical consequences of their work that might be an error. Fact is, some inaccuracies, they have more costly consequences than others. There's examples of this all the time. Some drugs have potentially lethal side effects, and they ought to consider that, even when they're testing them on small numbers of people. So scientists should not ignore the consequences of error. But evaluating the consequences of error cannot be value-free. Your moral values are very much involved in the evaluation of the consequences of being wrong. So values are integral to science. But does this threaten the objectivity of science? And that's a fair question to ask. So according to Douglas, no, values don't necessarily threaten scientific objectivity, okay? And it's just, there's right ways and wrong ways to use values. So, I mean, whether you like it or not, smoking causes cancer, okay? So values are not reasons to believe scientific claims. Whether you like it or not, smoking causes cancer. So there's legitimate and illegitimate rules for values in science. If you suppress evidence because you don't like the implications, that is an illegitimate rule for values in science. So for example, Exxon has known about the greenhouse effect since the 1970s. Their own scientists knew that increased greenhouse fossil fuel emissions would lead to more global warming. They know, and they suppressed that because it threatened their business model. Likewise, Big Tobacco knew about the cancer risks and suppressed that information as well. So that is an illegitimate role for values in science. Suppressing evidence because you don't like it, the implications, is an illegitimate role for values in science. Values only threaten the objectivity of science if they're used in their wrong way. So it's acceptable to pursue studies because the society values them. It's acceptable to be attentive to the social consequences of your work. It's acceptable to criticize studies that only benefit interests of one group. It's unacceptable, though, to reject data because it threatens your financial interests. So if you want to read more about this, I encourage you to check out Heather Douglas's work. The end.